Right. Hello, everyone. Thank you for coming. Nice to see everyone in person, and thank you everyone online. Hopefully people can hear me all right. Let us know in the chat. If not, we've got someone watching now. But yeah, welcome. My name's Matt. I'm a mechanical engineer here at Waterman's. I'm also the events coordinator for the HVAC group. If you don't know who the HVAC group are, we're a committee of volunteers headed up by CIBSE to try and promote technical excellence and best practice in the industry. So we get involved with running technical events like this, but also doing CIBSE guides and TMs and AMs and the CIBSE journal and all kinds of different things. So if you're interested in keeping up to date with what we're up to, then you can follow us on LinkedIn or subscribe to our mailing list on the CIBSE website. And if you're interested in getting involved, then come and speak to one of the committee members, or you can email us as well. But I will pass over very shortly to our guest speakers today. We've got Celine, who's here from ACOM and from the GLA to come talk to us. We've got Ankit here from Waterman's to give us a bit of background on one of his projects that he's working on. We've got Yara here, who's going to talk about TM65 and TM65.1, which he helped to co-write. And we've got Chris here from Mitsubishi as well, who's their lead zero carbon design manager, I think is the title. Yeah, close enough. And so we'll hear from all of them, and then we'll do a big Q&A time at the end. So if you do have any questions, save them to the end. If you're here online, then you can put them in the chat box and read some of them out at the end as well. But before I pass it on over to them, I just want to give a quick summary into what embodied carbon is and why we're talking about it. So whole life carbon is kind of what we talk about when we're talking about the entire impact on the environment of the building. It's kind of from cradle to cradle, all the emissions created. And you can roughly split it up into two groups. You can split it up into your operational carbon, which is kind of your ongoing emissions from electricity use and from heating buildings and stuff like that. And you can also split it into your embodied carbon, which is what we're going to talk about. And that's kind of all the carbon that's locked up and emitted during the construction. But you can actually break that down into a lot more. Sorry, it's a bit small, but you can split it up into kind of the raw materials and the emissions in extracting those and processing those, the transportation costs of getting the raw materials across the globe, the manufacturing, which I'm sure our panel will come and speak to later, because MEP systems are a lot more complex than just a brick. There's subcomponents and sub-manufacturers, so it's all very difficult to kind of get through the nitty-gritty. But the reason that we kind of need to start looking at it is because embodied carbon is only going to become more important. Up until now, we've kind of been focusing on reducing operational carbon, which is great because it's the biggest percentage. But as we kind of move towards low zero carbon heating and decarbonise our energy grid, that proportion of the total energy decreases. And if we want to hit our net zero targets, then we're going to have to start looking at embodied carbon as well. But that's enough from me. I'll now pass over to Celine. Oh, no, sorry.
Hi, so I'm Celine from ACOM. I'm also a whole life carbon officer for the GLA. And well, I was going to start off by kind of giving a brief introduction to embodied carbon, but I don't know how necessary that will be. Kind of going to start off with what a whole life cycle carbon assessment was. I think that's been touched on previously. I think kind of the important part about that is, I think when you're looking at the operational carbon, is remembering that it is kind of the local grid factor times by the operational energy. It's like change it, and then looking at what is embodied carbon. So this is just kind of touches on some of those modules or life cycle stages that Matt was talking about. So embodied carbon is more kind of emissions associated with the non-operation phase of a project, whereas obviously operational carbon is the operational phase. So it kind of starts from the extraction of raw materials and then goes through any manufacturing, transport emissions and any construction emissions. And then when you go through and you look at refurbishment and maintenance, they're kind of building in use emissions, and then looking at demolition and recycling. So what is this in context? Like this is all really good. What is it in actual practice? What does it mean in our calculations? It can be represented, those life cycle stages can be represented by the discrete modules of embodied carbon. So the kind of yellow square rectangle in the centre represents embodied carbon. So you can see you've got your product stage, construction stage, in stage, and end of life stage. So there are multiple things in this. So like transport, for example, is a consistent title that is referenced throughout the modules, but they represent different use stages. So the product stage or its construction. So product is the actual raw materials and that transportation to the manufacturer. And then construction stage is the transportation from the manufacturer to site. Now you can see from these like building modules, pink and yellow, that is essentially the calculation that Matt and I showed at the beginning, where it is the embodied carbon plus the operational, but kind of through the lens of those embodied carbon life cycle stages. And then the side we've kind of got circular economy, not really relevant, I think, especially for MEP kind of recycling is a bit hard, but something to bear in mind, and that's kind of a negative that's taken away from your overall whole life carbon. It's not really included or shouldn't be. And then I was going to look at the increasing influence of embodied carbon over time, same as looking at the moment. Obviously, if we take each of these circles as our kind of overall carbon emissions of a building, and how at the moment operational carbon contributes to a much higher proportion than embodied. And over time, it's going to change through grid decarbonisation, but also because we understand operational a lot more than we do embodied. So what are some of the trends that we're seeing? I think as a general one, we're seeing embodied carbon is becoming a lot more part of the conversation. We're seeing a lot more kind of building-wide whole life carbon assessments, but then also really interesting, a lot more specific MEP embodied carbon assessments. So whether that's on just a client wanting to look at what their embodied carbon of the system that they're proposing at one system, or a really interesting one that we're doing is we're starting to use embodied carbon as a metric to review different MEP solutions, particularly for refurbishments. But I think that needs to be taken in tangent with operational, but I'll touch on that more in a second. We need to look at why we're kind of seeing this increase in trend. I think for starters, the CIBSE TM65, that publication has really changed it. It's given us a way to understand and calculate MEP embodied carbon. But then GLA whole life carbon guidance, I think that has had a huge impact in just forcing people to actually do those calculations on a building wide scale. But in doing that, it's set a very interesting precedent. So we know that other local boroughs within London, for whole life carbon guidance is only applicable for variable planning applications. So those large scale type building applications, or if it's built on a particular piece of land like Greenbelt. But I think this is having a wide impact in terms of the industry. So like London, other London boroughs are becoming interested and looking at how they can apply this and how they can also look at doing this for smaller applications, as are many other local planning authorities across the country. So I think it's definitely something that's going to increase. And it's kind of linked to the next one, is the planning review metric. I think there's kind of an idea that this GLA is just a data collection tool, and it really isn't. It really is something that we are reviewing planning applications by. And I think a really interesting example of this, which I'm sure most of you will be aware of, is the M&S application on Oxford Street, in which the Secretary of State at the time stepped in and rejected the planning application purely on the basis of embodied carbon, which has set a very interesting precedent across the thing and given kind of an understanding that it really is an equal metric of which buildings are being reviewed on that. And then net zero, I think, is quite an important one. I think we're all aware of it. Both public and private companies have made net zero commitments. And as part of that, we have to reduce the operational and embodied as far as possible. So as part of the work that we've been doing, we've kind of highlighted established four key parts of MEP equipment which we think affect the embodied carbon the most. It's kind of starting with refrigerants, kind of the main one. The main impacts that we're seeing are both in terms of type and charge. So obviously the type affects the global warming potential, or the GWP, so the embodied carbon, and the charge, obviously the quantity. The more you have, the more embodied carbon you're going to have. But refrigerants is a particularly interesting one, I think, at the moment, because over the next few years, some of the really high GWP refrigerants are due to be phased out. I think that creates a really interesting idea and something that we really need to consider, particularly for MEP. In that, if you have an existing system and you just change that refrigerant, just a like for like, you might have to change a few little bits of equipment that might have embodied carbon impacts, but you're reducing your GWP of your refrigerant, so overall your embodied carbon is going to go down. But then what happens when you look at the operational side of it? If it changes that system efficiency, for example, if it reduces your COP, then you've had that reduction in embodied, but your operational has gone up. So that's something that we're starting to look at with clients, and an interesting thing for MEP and particularly for refurbishments. It's considering that kind of overall carbon. If you're not able to do like a full whole life carbon assessment, you don't have enough information to calculate each module, doing that overall assessment, even if it's at like a high level, stage 2, just an idea. And we're using that principle to review different design options that the engineers put forward for different projects. Another one that's really important is distribution routes. I think this is kind of more relevant to refurbishments because you might not be able to get that optimum distribution route that you would be in a new build. But both material and length definitely affect that. And then sourcing. So country of origin of your products, whether that be kind of your, I think from manufacturer raw products, but from my side, more the actual equipment. That affects both your transportation emissions and then also that grid factor that is applied to that, so be worse. And then weight of product. I think this is an interesting one. That lighter units, obviously less materials, lower embodied carbon, but then lighter units from an MEP perspective can reduce robustness and kind of the service life of that. And that touched on why it's so important from an embodied carbon perspective to do your calculations across a really consistent time period. So within the industry, we tend to use a time period about 60 years. That's because 60 years is the standard life cycle of a new build. But you can tailor that depending on what's appropriate for your project or for your model. But I think looking at items like the weight press, it's just so important to make sure you have that really consistent time period across all of your calculations. Very much. Sorry about the doubling up of content there. Let's go through it as quickly as possible.
Next up, we've got Ankit, who.
There you are. Right in the wings. Perfect. Good evening, everyone. I think Celine's covered very interestingly the challenges that we face as an industry when it comes to balancing operational challenges with embodied carbon. So today I'm just going to take you through one of the case studies and some of the work that we've been doing at McLoughlin. And it is the Edenica case study. So Edenica is a 13,000 square feet commercial scheme, and it's going to deliver a 12-story building plus ground, mezzanine and basement levels. It's primarily designed to offer a flexible working environment with a hub of the ground floor. Some of the key challenges that we faced in this was balancing the operational with the embodied. And we've taken some unique approaches to this, so much so that the project itself is able to now achieve or is targeting some very key sustainability benchmarks such as BREEAM Outstanding. It's got the first material passports deployment. It's well enabled and it's also been nominated for the ACE Best Net Zero Building Award. So, by using low carbon construction, building elements and using lean designs for the MEP systems, we were able to significantly reduce our embodied carbon emissions to about 30% below the current benchmarks. I'll walk you through what those strategies were later on in the presentation. And what we were able to do is by integrating passive design measures and using responsible building servicing methods, we were able to ensure that no fossil fuels are used in this building. And we're also able to deliver a low operational energy performance, about hitting 2030 UKGBC targets. So just to give you a few headlines as to what this building is able to do, it's fully electric, It's got mixed mode ventilation systems with underfloor heating and air systems. It also utilizes a passive cooling strategy to further enhance the building energy performance. And these are just some of the key sustainability highlights that we have. So just getting into the crux of it. So the first real approach that we've looked at was the fabric design. And as MEP engineers, I think this is one area where we have a lot of input to give, and it's difficult to get architects to kind of come and play ball because they have their creative processes, and we somehow kind of control that a little bit, and it's trying to get them to kind of understand what we're trying to do here. So while working with the architects, we were then able to come up with a mixed mode strategy, which optimized the use of natural ventilation, which helped our building loads quite a bit. The building itself has mid and high level openings to, again, maximize air circulation when possible. And then we were able to talk the architects into not having a full glass facade, but have a few shading devices to enable. I can hear a lot of laughs because I'm sure you guys go through the same process. And then obviously including some exposed thermal mass to, increase the heat absorption as part of the nighttime PERS strategy. One of the other elements we were able to discuss was to have slightly higher summer set points, and it's about us adapting to our buildings as well. It's not just the buildings adapting the environment. So that was one of the key issues to help reduce the energy loads. And as a passive design measures that were included, so the windows open automatically when the external conditions are suitable. Users can override it and shut it. The lower window is obviously manually operable and is monitored via contact. And then you've got the perimeter fan tile that reverts to recirculation mode from room to room when the windows are in operation. So simple strategy, and it's just to enable us with a better energy design. Now, some of the challenges that we end up facing is the fact that we're now having to convince, and while our industry is kind of convinced that we have a few set methods that could work, our main primary use is that when we're looking at a conventional Cat A fit out, if you go for a ceiling-based system, about 30 to 50% of that is either altered or removed by the tenants when they move in. That's a huge loss of fresh material, which we try to avoid by applying solutions where we can take that decision away from the tenants a little bit. And if you think about it, over a building life cycle of 60 years, we're looking at some significant replacement taking place. So the embodied carbon will only grow after that point. And with a ceiling-based system, you've got more moving parts, which means you're going to have more replacement, which again is going to add to more embodied carbon. So the underfloor air distribution system is primarily the approach used at Edenica, where what we're trying to do is, again, like I said, reduce the number of alterations, take that decision away from tenants, where they can only just focus on the lighting and the diffusers and the detectors, depending on their layouts. It gives them a lot of flexibility as well in terms of how they want the internal layout to take place. And because obviously there are fewer moving parts, you've got significantly lower replacements. So we are able to tackle the embodied carbon side quite significantly by taking such an approach. Just to show you exactly what that was able to deliver, you've got a typical office building here, and we were able to reduce the upfront carbon by about 37%. In terms of whole life carbon, there's significant gain as well. So it's one of the approaches that you can apply when you're trying to balance both the operational side and the embodied carbon. Thank you so much for listening.
So we have Yara.
So I'm going to be talking about CIBSE TM65, CIBSE TM65.1, and then also giving a bit of a sneak peek into TM65.2. So all about the methodology of calculating the embodied carbon of MEP, and then just some research study examples and kind of the findings that we've seen in the past year or so. That's just going through the agenda. Skipping past the definitions, going straight into the importance of considering building services embodied carbon and whole life carbon assessment. A few of these I think Celine touched on as well. First of all, the quantities. So it's something that I think it's sometimes hard to perceive what the quantities are. It's something that's hidden. It's underneath ceiling voids, underneath floor plates. But really, this kind of figure that we always use from the Carbon Leadership Forum. A 2,000 square meter office can have roughly 25 tons of MEP equipment, which is a massive amount. And the quantities that go into that are all made of high impact materials a lot of the time. So metals, which have a really high embodied carbon coefficient, aluminium, rare earth materials, electronic components, all of these really have massive contribution. As well as that, the high replacement rates. So we usually use CIBSE Guide M, looking at the replacement rates of the MEP equipment, and that's roughly between 15 to 20 years on average, could be even less. So when we compare that to the structure of the building with the skin, that sometimes can withstand up to 60 years. You have to consider over 60 years how much replacement is going into the MEP. And finally, refrigerant impact. So that's massive, and it could range depending on the impact choice, the refrigerant selected. So all of this led to developing CIBSE TM65 and the methodology to kind of calculate this gap that was found. And you can see here on the left all of the life cycle stages that are included and covered in the TM65 calculation, either by a scale-up factor or having kind of fixed figures that you can use within the calculation. So CIBSE TM65 has kind of three main steps to it. First of all, the data collection, in which we need some support from manufacturers to complete that, and then doing the calculation. So that can be done in one of two ways, either a basic calculation or what we'd call a mid-level calculation, which does need a bit more involvement from manufacturers and information on their supply chains. And then finally, the reporting. So depending on the type of calculation you do, you can either report it in the basic reporting form or mid-level. And within the TM65, we thought it would be really important to do this comparison between those two calculations and EPDs. EPDs have a standard methodology of calculating the embodied carbon of materials and equipment in general. And that's something that throughout the document is kind of reiterated as super important. The first step, always to ask for EPDs, and that being kind of the source of data to use, just primarily because of how detailed they are. You can see in comparison, CIBSE TM65 was created as a more simple and quicker approach to kind of bridge that gap while EPDs became more of a norm. And just to show an example of what the manufacturer form looks like, what it's broken down into, there's three main sections. Section A is essential information for any basic calculation, and we need up to 95% of the material breakdown in order for it to satisfy the requirements of the calculation. Supplementary information, as mentioned, it needs a bit more about the factory energy use, most importantly, so where is it coming from, and that will help you to get a bit more detailed number. And finally, section C, which is kind of an optional information section that's to do with the development of TM65. As we know, it's quite new, and we could always include more about water consumption and waste output in the development of the document. Quickly to show the overview of the basic calculation method. So you can see this calculation method includes a scale-up factor, which covers a lot of the life cycle stages. That's mostly to do with the fact that it's much more straightforward to do. So you don't need as much information. Multiply that by a buffer factor and then add on refrigerant leakage at the end. And in comparison to a mid-level calculation, you can see there's different steps for all of those different life cycle stages included now. The scale-up factor is removed because we no longer need it. We're covering for the life cycle stages. Again, including the buffer factor for any fixed numbers that are being used, like grid emission factors or transport distances, for example, and then adding on refrigerant leakage. So that was a whiz through TM65, and now a bit more about how this was applied in an actual research study that came soon after, called TM65.1. And what this study was, is it looked at the embodied carbon of residential heating and hot water systems. So we looked at 30 different products. So you can see down here, from heat generation, hot water distribution, heat emitters, looked at valves as well, the pipes. And we applied this into 13 different design strategies that we see commonly amongst residential schemes in the UK. So just to shout some of them out, air source heat pumps, direct electric, active ambient loop, passive ambient loop. So we calculated that across the schemes. And to make sure we understood the scale of how this could be expanded, we looked at 4 different residential typologies. So as small as just one terrace house to a 2,000 unit development of 10 blocks of 200 units, just to see how these compare to each other, depending on the size of the scheme. And some context of the building fabric. We used the ultra-low energy building fabric, similar to passive house level. The reason for this is, this guidance is really pushing towards what we want to see and what we want to be designing all new builds to. This is why these were the figures that were used, which are typically what we're trying to push for amongst all new schemes. I'm breaking down the process of how we completed this research. It was broken down into two main phases. One, which was the product level, which is getting the information from manufacturers and doing the actual calculations, and then bringing that into the system level. So those 13 different systems, we needed to use, the heat pump component and the valve component and the emitters, and adding all those together to, the right quantities and creating the system level results. So for our study, we had 29 manufacturers involved, which was great to see for a publication that was new at the time. And we were able to get 70 different data points to include in our calculations. And from this, you'll find in the document towards the end, you have 2 pages for all of the different products that we included, and these kind of 4 standard graphs that show the results of the capacity by the kilogram CO2 by capacity. We brought in the weight capacity data points as well. And then you can see the buckets that we used, because each bucket created a generic data point that we could then use in our system level calculations. And these dotted lines also represent the generic data points that were calculated for our system level calcs. And this figure is included as well that shows amongst all of the range of, from the heat generation to the really small valves and the ventilation equipment, what's the average that we found, and it was roughly 9 kilograms CO2 by kilogram. The weight is just the constant across all of the different materials. So we're able to create this graph to show how they were all comparable. Some conclusions from our system findings. So as mentioned, we were able to create generic data points. The way that our system level calculations were calculated, we're getting the quantities of all those materials, multiplying them by the TM65 product result that we got, using CIBSE Guide N to calculate the replacement during the study period. How many times are we changing the air source heat pump? How many times are we replacing the radiators? And then finally adding on the refrigerant impact across that whole study period. So this is an example here. You can see these are, for example, the components of all one type of heating and hot water system, having the quantities, the capacities, using all the generic data points that we had, multiplying by the replacement, and then the refrigerant leakage across that. As well as the 2-pager on the different products, we had pages on the different units. So you can see one for a terraced house, one for a 100 unit, one for the 200, and then one for the 2000 unit scheme. And what that shows is all of the different heating systems and their results, showing the minimum, the average, and the max of what we could see for all of those different materials. And then also highlighting the top 3 impactful elements of each of those systems as well. So there's double pages on each of those. There's 4 in the document. The first and most obvious one is that the embodied carbon of heating systems matter. So we could see this range between 3% and 25%, which is a massive amount. If you're looking at, it could be up to 0.25% of the embodied carbon of your whole project. And this is also to point out that this is just the space heating and the hot water above the MEP. So if you're bringing in cooling, if you're bringing any additional MEP, that's also going to contribute even more. And again, that there's a really big impact variance between your type of system. So it can be as low as 26, or if you're looking at a VRF system, possibly with a really high refrigerant, you go all the way up to 832. So there's a really huge variance, and we can't just use a standard, X amount of kilograms CO2 per meter squared on every project. And also that the refrigerant leakage is really significant. So if we're looking at maybe LECI targets, GLA targets, all of these include a certain X kilograms CO2 per meter squared. In this specific case, we're looking at a LECI target. This 832 would be above our current building target. And just to call out, the refrigerant that we used was R134A, which is not even the highest refrigerant warming potential that we see. So pointing towards the refrigerant leakage, we do have some complementary studies in the document, and you can see here that making a better choice of your refrigerants that are used, like R32, that could bring it down massively. Again, there's other implications or ways to consider. Good building fabric reduces the embodied carbon of your heating system by 40%. So in this example, we have building a business as usual fabric versus an ultra low energy, and just, you know, by insulating more, having better fabric, you can see obviously the MEP equipment could be sized to a smaller increasing the thermal performance of the building fabric can balance out the increase in embodied carbon. So you might have noticed in an earlier slide that the gas boiler and the air source heat pump was, the gas boiler was lower than the air source heat pump. But in the case of actually improving the fabric and having ultra low energy fabric, you can see they're actually matching up. And more than that, if we're bringing in the operational, of course, an air source heat pump is going to be more efficient. And finally, on that point, both operational and embodied carbon need to be considered in order to make a whole life carbon decision. And that's really important to just keep in mind when you bring this diagram together and add in the operational of the gas boiler. And just to wrap up, a couple of slides on CM 65.2. So this is a document my colleagues are working on at Atlanta, and this is an additional document which is looking at the embodied carbon of commercial schemes. So it's bringing in cooling as well. It's looking at a 10,000 meter squared office space with, you know, really good fabric, a specific occupancy ratio, and it's due to come later this year. We're hoping winter 2022, and we're starting to see the first kind of graphs of what that's forming. Similarly to the one I showed for TM 65.1, you can see the full kilogram CO2 by kilogram for all of the components used in this study, which is wider. So chill beams, for example, is a new one that we didn't cover in the residential schemes. And that is all. Thank you, everyone.
Thanks very much, guys, for inviting us in to talk to you all today. As I said, my name is Chris Newman. I'm our Zero Carbon Design Manager, so it's my job to try and find novel and unique ways of applying our product and then understanding how that impacts on the designs that you guys are all trying to deliver. And obviously today, specifically around the topic of embodied carbon. So what I've tried to do in this presentation was be a little bit selfish and look at this topic from the point of view of a manufacturer, which is not always necessarily in perfect alignment with how designer might look at it or how a client might look at it, but obviously we've all got our own commercial pressures, and one thing that is quite important to bear in mind as a manufacturer as well, we don't just make products for the UK, we're making products for the whole world, and for different markets there's different pressures in different areas, different legislation, things that we've got to deal with, and obviously the UK is a really important market to us, but it's not always leading the way in every area. So we've been looking at ways as a manufacturer to reduce our emissions production for a long time. We've had significant target reductions that we've been achieving. You know, we're trying to actually build products with zero emissions in our factories. We're trying to also find ways that we can actually build product that's able to be recycled easier, dismantled easier, and also to use less amount of virgin resources when we build it in the first place. I've just picked out an example from our environmental sustainability vision for 2050 there, which just goes to show we've been looking at how to reduce the size and weight of the products, which I think Yara mentioned specifically before, Celine, about trying to make them more recyclable. So it's not something that we've only just started to do. This is something that's been ongoing for quite a while, and we're looking at it in lots of different areas. I mentioned before, obviously we don't just work in the UK. If you take the European market from a manufacturer's point of view, it's usually the market that has the most amount of legislation, and it's typically the market that tends to move forward first with environmental concerns. As a good example of that might be something like the Energy Related Products Directive, the Eco Design Directive, which I'm sure you guys will be familiar with, about driving the efficiency of products and then making manufacturers display and demonstrate what the efficiency of those products are on an even metric. Well, there's actually some legislation that's coming in France at the moment called a Product Environmental Profile, PEP, or you might also see it as the Eco Passport is the other terminology that's being used for it. This is now coming to legislation in France from earlier this year, and it's actually requiring manufacturers that supply products into the French market to actually document, understand and display raw material makeup of the product and the manufacturing and the packaging that goes along with it. So you can see there's some real similarities and alignment to what we're looking at today from an embodied carbon point of view, albeit through a slightly different lens in the French market, but nevertheless the raw data from a manufacturer's point of view is pretty much the same. Obviously, as a manufacturer, we've got to decide, where do we put our effort, where do we spend our money, where do we try and make improvements. And when there is actual mandatory legislation forcing us to do something, if we want to sell a product in a particular market, that makes it a lot easier for us to implement change and to make a difference. When it's only advisory, it's not always easy to follow the latest guidelines when there's only advisory guidance. So having the Eco Passport in France has been really, really helpful, because not only is it given us requirements to start producing this information for the factory, but it's also started to allow some sort of standardization and some alignment about things like, what's the product life cycle? How long do we assume that it will be in operation for? How long do we assume that it will be transported in distance from point A to point B? CIBSE TM65 was really helpful for that as well, because that provided some assumptions, but at the moment there isn't kind of standardized assumptions in every area, and obviously that's been a challenge for us to try and produce data when we haven't really got a full complete set of standardized assumptions to work from. But as I say, the PEP has provided a really good baseline for us. So we are and have been in the process of trying to produce an EPD for some of our products. I'm sure hopefully you guys will be pleased about that, but I just thought I'd try and map this out, because people kind of think, well, why can't you just go and get EPDs? Why hasn't everybody just got EPDs for all of their products? And oh, sorry, when I'm talking about an EPD, I'm talking about an environmental product declaration. We've actually been on this journey for about 2 years. So back in early 2020, as a business, we were deciding, well, should we do this? Is this the right thing that we should be doing? It's not legislation, it's just guidance, but maybe it'd be a good thing for us to do. And then, of course, as you see, we kind of had the pandemic that kicked in, and that obviously reduced the number of members of staff in the business, and there was a lot of other priorities that kicked in during that time. But we still felt that it was such an important topic to move forward on that we carried on with it in the background right the way through late 2020, when we actually started to engage with some of the independent bodies that are able to actually provide EPDs for products, and BRE was the body that we started to talk to. And then over a period of 2021, there's all sorts of things that need to be defined. Do we want to do a cradle to gate assessment, just from the product up until the point that it arrives on site? Do we want to do a cradle to grave assessment right the way through the whole product life cycle, and then the recycling of the product at the end of its life? We've then got to go and talk to our factories. You know, we make products in Japan, in Italy, in Turkey, in the UK, and you know, all across the world. We need to go and engage with all of those factories to make sure we can even get the information that we're actually looking for in order to produce the EPD or even the TM65 calculations that we're talking about. And then obviously the bodies that we were talking to had never really done this before for complex MEP products. So there was a bit of a discovery piece that we were going on together, where we're effectively asking somebody to do this for us who's not done it before. So we're sort of traveling along that journey together. And then really helpful, obviously TM65 was launched in 2021. We started publishing TM65 documents on our document library. Then we did some webinars. Hopefully some of you guys might have attended them, where we shared some of our homework on what we've been doing. But then right the way through 2021, it was a case of checking, verifying data, making sure that the information we were getting from our factory was accurate, verifying that with our EPD provider, going through checking calculation methodologies, understanding the impact of a small little decision, that a piece of data that we might provide, what impact does that actually have on the calculation? Should we be given absolute worst case scenarios? How far should we assume products have been traveling for? So obviously we're quite a conservative manufacturer, so we were always trying to make the worst case assumption in every possible outcome to make sure that no matter where we sold the product in the UK, no matter how you wanted to look at it, we've covered it. It was a worst case scenario. And even then, once we got to the end of that, we've made all of those safe assumptions. We've then still got to analyse all of the data and analyse all the results and decide how we're going to display those results, how we're going to produce that document. And obviously, as we stand here today, you know, we are in a position where you know, we've got a draft document to look at. We're deciding what we're going to do with that, when we're going to launch that, and then as we've got to go through the independent verification process. And I just wanted to kind of express to you guys that it's not just as straightforward as going, oh, let's go and get an EPD, and then a couple of months later one appears. It has been quite an interesting process. And I think the other thing that I wanted to mention as well is we make a box in this example, and we supply that box, but a box is part of a system. And I think Yara mentioned this before in her presentation. When we concentrate only on the box that we make, and then maybe we don't look at how that box is then implemented into a complete system, we can actually be concentrating maybe on the wrong thing. Or we could certainly be thinking that something was particularly good when actually when you install it in practice, it isn't particularly good. So as a good example, TM65 didn't look at the site added refrigerant charge, and actually neither does an EPD. Because an EPD doesn't look at a site added refrigerant charge, because who knows how long the pipe run is going to be, who knows where an outdoor unit is in comparison to an indoor unit. And I think Celine also mentioned before that the impact that refrigerant can have. So we did some makeups to try and give you guys an example of this. On the top here is a traditional R410A refrigerant VRF air conditioning system, heating and cooling system. And that has refrigeration pipework from the outdoor unit through to a distribution box, and then refrigerant pipework continues onto every fan coil. And we've assumed a kind of typical pipe run from an outdoor unit to a box, and a typical pipe run from the box to all of the fan coils on a typical sort of size system. So these are all 30 kilowatt capacity machines, with, in these examples, 8 4-kilowatt ducted units connected to each one. And that gives us a total embodied carbon for that solution of I don't know if you can read the numbers on the screen. There's 49,655 kilograms of CO2 equivalent for that particular system. Now, if we simply change the refrigerant in that system and provide you with exactly the same VRF system, but use a lower GWP refrigerant, in this case R32, then obviously we can significantly reduce the overall embodied carbon of that system when we include the site added refrigerant using the same pipe run assumptions. In fact, the saving is quite significant. You see there 60%. But we can go even further. We could offer a hybrid VRF system where we have refrigerant pipework from our outdoor unit to our box, and then water pipework from our box to our fan coils. So again, repeating what the other speakers were saying, we found a way of being able to not just reduce the GWP of the refrigerant we're using, but then also reduce the actual volume of the refrigerant that's in the system. So there's also far less joints in the system, so there's much less likelihood of leakage. And again, that's one of the other assumptions that we've got to make about what the assumed refrigerant leakage on these type of systems is. So I've done a breakdown just to show you the impact of the different elements of that system. So here you can see the actual outdoor unit, which has got a factory refrigerant charge in it. They all come from the factory with an element of refrigerant in it. And you can see there that nearly 2/3 of the embodied carbon of the outdoor unit is just the refrigerant charge that sits in it. The small bit is all of the manufacturing of the steel and the aluminium and the copper and the motor and the compressor and the fan motor and all of the other things, and the actual energy we use in the factory, and the transportation of all the raw materials to the factory, and the transportation of the product from the factory all the way to the UK. Still only makes up a very small proportion. Then we've got the branch box, which is this one here, and you can see this kind of light blue colour is the additional site added refrigerant charge, and then so on with the fan coil units connected. When you look at it as a total makeup, you can actually see that the refrigerant does have by far and away the biggest impact on the overall system. And this is where we as a manufacturer need to really work with you guys to better understand what actual leakage on site is, because some of the assumptions are, from our experience, they seem rather high, and the impact that they're having on system calculation seems to be skewing it a little bit. So I think we've all got some work that we need to do on getting those assumptions to be a little bit more accurate. And all of those numbers, by the way, we've broken these down for you so that you can see what they all are individually as calculations. I'm sure that Matt will probably share some of this information with you guys afterwards as well. But finally, just to finish off, we are trying to share our homework really with this, which I think is where everybody is on this topic at the moment. So we've just launched our guide to embodied carbon in the built environment. The QR code is there if you want to download it from our website. But what we've actually done is published all of the data for pretty much, I'm not going to say all of our systems, we're doing as many as we can, constantly updating it. This is everything we've got up to now. And what you'll notice that we've started to demonstrate, maybe if we've worked it out for one product and then we've scaled up or scaled down. from that one product, so that you can see where the raw data is originating from, and then how we've scaled up and scaled down. Again, as one of the previous speakers mentioned about using the weight of the product, we can proportionalize the total amount of embodied carbon, which is the same method that's used in the product environmental profile eco passport in France as well. So I'm hoping that I haven't overrun too much, Mark, and I'm also hoping that some of the information that I share with you guys there gives you an idea from a manufacturer's point of view about some of the complexities, some of the nuances, and some of the difficulties that we've got. But hopefully we can keep sharing our information between us all. We can try and get some better data and then make some better decisions on the buildings that we're building. That's all for me. Thank you very much.
I hope everyone's found it interesting, and I hope we've also got some good questions coming up. So I know you've just gone and sat that down, but can all the panelists please come back up, and we'll just swap the people online over so they can see us. There we go. Perfect. So, does anyone have any questions? Put your hand up. Paul.
Someone else mentioned it earlier, where you've got to go and waste so much carbon on the system. When you're installing, say, long refrigerants, they need to be adapted. Do you have ways of drawing down refrigerant in charge of the Cat A system being adapted? The Cat B system that generally just get wasted.
No, typically what would happen, refrigerant will be reclaimed from the system by a qualified person with the FGAT certifications and the safe handling refrigerant certificates, etc., that are required to handle refrigerant by on-site engineers. They would put that refrigerant from the system, store it, continue whatever alterations were required, and then typically recharge that back in. You might find that as part of that Cat A and Cat B, you might have a change of the length of pipe run. The refrigerant charge needs to be recalculated. You might find you do need to add additional on top. You might find you don't. But yeah, it's not simply throwing it away at that point. Well, a big part of the certification that's required in order to be able to handle refrigerant is all about not having that loss. It's about being able to safely and correctly remove connections to a system, remove refrigerant from a system using the correct tools and methodology so that there isn't leakage from it. Obviously, it is a manual process, a mechanical process effectively, but you know, the whole purpose is that anybody who is doing that is trained and certified, and therefore you know, loss shouldn't really occur.
Anyone else? Yeah.
Hello, Chris. Are there any other refrigerants beyond R32 that, especially you're looking into, that reduce the GWP of refrigerants we put in VRF systems that are being researched, or maybe not in 5 years, but 10, 20 years?
No, absolutely. I mean, in answer to your question, R&D, you know, is a massive part of what we do as a manufacturer to try and push that forward. A lot of the problems that are generated by changing refrigerants is that, again, I think one of my fellow speakers mentioned it before, sometimes changing a refrigerant can have a negative impact on efficiency of the system. I mean, a very good example is that we've, you know, fairly recently moved from R410A refrigerant as the predominant refrigerant in DX systems to R32, which introduced a flammability issue that wasn't there previously with R410A. So although the GWP has been significantly reduced, an additional problem has been, you know, introduced. We have problems, you know, maybe as we reduce from R32 down to other refrigerants. Good example, we could use CO2, not necessarily in a VRF system or in an air source heat pump, for example, which has obviously got, you know, the lowest GWP of 1. But that then has problems with pressure, problems that may well require additional safety measures to be taken. So everything is a balance and a trade-off. And I think at the moment, when with regards to development on that, it's trying to find a good solution that doesn't impact so significantly on the way that things are currently done. So a good example, I think Yara, you mentioned R134A refrigerant earlier. You know, we've managed to adapt to a new refrigerant called R5138 as an example, as a replacement for R1348, which is much lower GWP, from around about 1400 down to about 600. So there's some positives in there, but unfortunately it takes so long to develop new refrigerants and then products to suit them. It's not the type of thing that you'll see a new one come along next year and then a new one come along a few years later. It kind of takes years of development. I think what we really need as well is a lot more certainty on what the things like F-gas phase down changes are being talked about at the moment, about the potential acceleration of the phase down of fluorinated gases. There's some other safety things that are coming in. Without knowing exactly what the long-term picture looks like, it's difficult to know where to sort of invest and where to try and develop, really. And again, as I said before, it's not just the UK or European market that we're building product for. The Asian market, American market, they've all got different pressures. So I think the long answer to your question is you'll have to wait and see. But it will come along eventually, and it will continually reduce in the right direction. But I haven't got any sneak peeks I can give you right now. So
any others?
Yeah, and question for Yara. Obviously, from a manufacturing point of view, this I know you're actively that's to be provided with the embodied carbon data products. But you made the point, obviously, interested with the life of the building compared to typically the life of plant, and potentially be looking at overall loss of plant replacement. Do you see many manufacturers? I mean, or would you be expecting manufacturers to be looking at ensuring that their products items can be replaced within product, rather than, because I think historically a lot of products just get pitched when it comes to 15-20 replacement. So you see that it being.
Before you answer, can I repeat it so that people online can hear?
Yeah.
So the question is regarding do manufacturers or should manufacturers be looking at the I guess maintainability and replaceability of parts of kits to help minimise the embodied impact in terms of when plant comes to the end of its life?
I think that's definitely important, and it's something we're speaking about earlier today, just about, and it's not just specific to MEP, but the whole building in general, just looking at it as a component that can be disassembled and reused in different ways. Every material has a different level of reusability or recyclability. So within a component, if there are ways we can use, dry fixtures instead of wet fixtures, and components can be disassembled, that will allow, the ones that can continue past 20 years can be reused. The ones that can't can be recycled or disassembled in a way that makes sense. So I think that's definitely something that would always be encouraged, just to continue the circularity of building materials and MEP equipment use.
Well, I have a question that's, I guess, more of a discussion point for you all. So we've got Part L that regulates operational energy use, or attempts to. What would be your opinion on a new approved document that helps try and regulate embodied carbon? Is that a good idea? Is that just completely impossible to introduce the EPDs that we've mentioned? Like, what are people's opinions, I guess, on embodied carbon building reg?
I can give you our thoughts on that. We would welcome it, purely because anything where there is at least a framework of standards that you're trying to achieve and you're trying to work to, it gives you something that you can build towards, work towards. Whereas at the moment, when things are unclear, it's difficult to know exactly what to aim at. We were talking as the three of us actually before, and about projects where we know that embodied carbon has got really strong drivers on a project, but it's then really difficult to measure solution A versus solution B because there's no standardized metrics for those two. Maybe we could use the M65 as an example, but it's difficult without standardization. So I think I'd welcome it purely just to set the standards.
I think it's definitely something that's in the works, but I don't think it should happen too soon. Maybe a bit different, just on the perspective that if you look at the benchmark at the moment, a lot of projects just aren't achieving them. So if we did turn that into legislation and we turn from a GLA perspective, turn that into a target, and make buildings have to achieve that or penalise people for not achieving it, when it is quite clear, given the kind of conversation that embodied carbon of MEP services is still so unknown. So in doing that and setting that target, are we just essentially cutting someone's legs off? Project plan. So I think, yes, it needs to happen and it should happen, but I think in time. And I think there needs to be a greater level of data collection more generally across the whole building, understand that, but particularly from an MEP perspective, really understanding like what percentage that actually contributes to on a building. Because at the moment, I think we were talking about earlier, about 20%. What is 20% of this building? The value. Where does that actually come from? What is that value actually representing? It's not real. It's based on so I think a cautious yes, but in time.
I think just to follow up on that, I think the biggest challenge facing is the fact that at the moment we've focused on the upfront carbon to a large extent. We haven't unpacked modules B and C and D, and those sort of elements, when we start looking at it from a carbon accounting point of view, it'll start to balance a lot of elements off. And I think that's not happened as an industry. So to start to benchmark it, like Celine's saying, it would be very difficult because the second-hand market or the recycle market hasn't really caught on yet. So you don't really have the avenues to offset after a point, and then you then force to go down an off route with carbon credits and the rest, which is not a permanent solution. It's just going to be an accounting. Yeah, exactly. And within 2 or 3 years, that'll stop making a difference. And I think that's why Part Z really should wait a little bit till you start to get this sort of research going and the data is collected, because we don't have any benchmarks that actually make sense when you look at modules B and C.
I think that really is happening at the moment. So there's modules B and C. I know there's some kind of consistent industry-wide assumptions that are being made of being used across projects. But given we're now kind of the second iteration of the GLA whole life carbon guidance, we're almost at the point in maybe a year or a couple of years or so where we're going to actually start getting some post-completion reports through, and then we can actually understand how those assumptions have lined up with what has actually been built. And I think from there, that will that's as you're saying, that we can actually produce some worthwhile, hopefully, better targets. Yes.
I could just add one more thing on that. I think we can think of it as kind of one thing making it mandatory to calculate, and that's for the purpose of having data, which is essentially going to get us to our goal. And the other thing would make it mandatory to be below the specific target, which is more challenging given that it's something that we still don't have full transparency on what the benchmarks are. So I think having it as something that maybe needs to be calculated is important, and I can see it being important through the design process. So if you're at stage 2 and you're calculating embodied carbon, that allows you to then later on in the design stage look at other alternatives. What can we do to reduce embodied carbon? It might not necessarily get you below, something like 500 kilograms per CO2 for your project, but it's still, you've still made a good decision to know, the embodied carbon of this specific material, we can use this material instead and reduce it. So you're still making the right decisions by calculating it in the first place.
So make the methodology of calculating it standard, and worry about setting the target after we've got enough data from the standard calculation methodology. I absolutely agree with that.
Awesome. Do we have any questions from online? We do. Awesome. One. Amazing.
In the CIBSE 65.1, there was a graph for all on the mechanical plant and their embodied carbon. Is there a graph that also adds / shows the operation carbon for those individual mechanical plants?
So in the appendix to the document, there are complementary studies. I believe so the scope of it was primarily on embodied carbon, but I think for an air source heat pump, I think a boiler was taken as the baseline, direct electric. So there were a few that were taken, including operational carbon, but not a copy of the graph for operational carbon. That was kind of beyond the scope of this assessment.
Yep.
Biggest carbon savings are made in project decisions for commissioning, counter cooling, collection of data, say pre-plan is pretty important. How do we share it better so we can convince clients we don't need to go additional? We don't even need to do this to performance based.
So that the question was basically, you need to make decisions earlier on in the design stage in terms of air conditioning versus comfort cooling versus nothing, and how can we better share data and I guess case studies to try and inform clients into which decision they should be making.
I think from a state's point of view, that is, I agree with you, it's one of the key challenges, and I think that's where building simulation does do a big role. Getting that in early on, just to give you indicative ideas of what your building orientation is going to do, what your glazing ratio is going to do. It helps you select the right kind of tools for servicing the building, and I think getting that model in early makes a big difference. If I was to give you an example for a residential building, if I were to use, and especially with the Part O kind of guidance coming in and forcing that direction a little bit, if you don't get it early and start to look at it, you're playing catch up, which is next to impossible once the facades are fixed and the rest, and you're going to end up with horribly overheating, rooms and the rest. It comes down to getting that simulation in early. So the twin buildings kind of approach, where you start the digital twin a little early on, and that kind of guides the design process. And that's something we have to hold some of the architects a little bit, but you know how difficult that can be. So. Exactly.
I'd sort of add into that about comfort levels as well, because historically, like, comfort has been an unlimited currency you can have within reason, whatever you want. If you want 21 degrees when it's 40 degrees outside, that's fine. You can design your building to do that, or vice versa in the winter. I think it's got to come from both sides, that the client who wants to try and achieve those lower embodied carbon emissions and the lower operational carbon emissions, they have to accept a more flexibility in terms of what level of comfort they're actually willing to accept in the building to get to the targets that they're trying to get to. Certainly when it comes to things like energy use intensity, to try and reduce that as much as possible. So I think there's definitely a two-way conversation to have a little bit there.
I think from like the perspective of having that data is like sharing in the industry. I know from the GLO sector we're doing collecting data, but that's not kind of applicable really to that small scale. But I know that CIBSE encourage everyone to send in any TM65 results with that database.
Yeah. So that is, that's the next step in the hopes to have a database. It's not supposed to be something that everyone takes for their own project and uses. It's something we can collectively benefit the industry with. So CIBSE always encourages any reporting forms, TM65, we welcome them. That goes to build the database. And I guess on that point, just to reiterate, it's a kind of fabric first approach that comes to step one. So I think that focus with adapting to kind of future climate scenarios, looking at solar shading strategies, that's always going to be the first step, and then cooling system will be considered afterwards.
Yeah, I'll also jump in to say, because otherwise Jen's going to kill me. Letty also does group where you share your results and your information. So if that's something that you're interested in, that's available as well to help share with data. Are there any other questions? Yep, Chris.
Christine, I'm fully aware that it took us 20 years to realise the performance gap between all our aspirations at design stage and delivery. And it's great that GLA's BC. You may have a Letty link there, but the idea that we hit tender stage, we have a very fragmented construction process, and we end up handing over to others. The idea that at the moment, I've heard a number of occasions developers say, well, actually we can renegotiate the carbon targets and these whatever, because there's a viability issue here. Does perhaps reinforce what you guys are talking about? This is data gathering stage, initial stage of this process. Got a hell of a long way before we can nail any projects, any more than we can actually nail unregulated energy, or even plug the fact that commercial buildings SBEM allows us to use unregulated energies to deliver on our regulated heating. Those flaws all over the place. Do you think, though, that the market is actually up for seeing the benefits overall, wider market as opposed to us in that hub, of how it makes better buildings? Because at the moment, we are tending to talk a little bit theoretically. Now, this might be a little bit open discussion, and let everybody else have their specific questions. I'd be interested hear what each panelist.
I think that's quite interesting. I might tackle it with a dual perspective on that. That's all right. I think there's definitely a big driver in terms of reducing operational costs. I mean, it's coming from a different direction, but that kind of pressure is very real on a lot of projects. And you can see in those projects, you tend to achieve clients a lot more readily available to achieve those targets, purely because there's a cost linked to it. Housing associations and housing groups are usually quite sharp on it, and they need it. The other thing that's really driving this from the other direction is client ESG targets. And while we all know they can be a little fluffy, the funds that are raising these, the hedge funds that are coming up with this, they are a bit more serious about it, because they can't raise the money if they don't actually deliver on some of these very strict targets. And it's good to see that changing in the last few years. It's not there yet, but I think you might start to see a bit more pressure on that front. And if your building doesn't achieve its carbon targets, it means their portfolio doesn't achieve the carbon targets, which means they are not able to raise the same amount of capital. So that linkage is very, very useful. So these were two key drivers that have emerged, especially this energy crisis has definitely highlighted these in a big way. And as far as the rest of it is concerned, I think there is a wider appetite growing purely because of the current general market scenarios that you can see. So I think it's not all doom and gloom yet. I think there's some positive moves in the right direction.
It's self-policing, isn't it?
Yeah.
It's become self-policing, which is a good thing, because the industry wants to do not just the right thing, it's trying to do the right thing ultimately leads financially to the right thing, as you're saying. So it would be great to have more standardization of that, so that it was less ambiguous and maybe a little bit less wriggle room. But obviously you don't want to regulate too much of these things to still leave room for innovation. But yeah, I think at the moment we're seeing huge demand from clients to basically to share homeware. They just want the numbers. They just want to understand where it is, which is perfectly with what the GLA is saying with BC. Everyone just wants the data. They want to know right now. So maybe there is a time lag between once all our data is collected and then where we set targets. But in the meantime, I think it's self-policing.
That's the kind of ESG things that focus on those very specific targets is kind of driving it in the wrong way, because I think there was this idea that, although I know we've spoken about it quite a lot in terms of operational needs to be considered with embodied and vice versa, operational is much more well established, whereas embodied carbon at the moment is still just an estimate. And I think that gets forgotten and that gets lost, particularly when you've got ESG as a driver for a client. It's that, what is this number? And it's not, and I think people get caught up in it. It's not, I'm not, in our reports, we're not saying that this is exactly what it is, this is exactly what it will be when it's built. This is our estimation at the moment. By and large, it's better than this. Kind of line in the sand type things. I think we do get a bit caught up in conversations that it is very developed and we are doing so much in it, but it is still an estimation. And I agree with the building performance type thing. That's something that I think is really going to hit embodied carbon very soon, particularly as kind of tools like one click become more and more prevalent, because you can basically go on and pick a really low EPD reality build. You that's a tool, pay for it. Yeah, it'd be interesting to see, I think, over the next few years what happens with that. It's definitely something.
It's interesting because I feel that one thing which was talked about, which will be most significant, as Caroline was given by DRC, is your reference to the amount of material that goes into our buildings. That seems to be a win-win all the way around. Bring less into the buildings, means cost come down, which then means developers and funders and so forth. And if you can then align it with these things, you begin to see positives which serve win-win-win.
I think that links to the ability to take out components and change them, particularly. I think they were talking about embodied carbon in this. There is a very big link to circular economy which needs to be considered, and I think if you don't kind of consider them hand in hand, we're really not going to get anywhere. We're just shouting numbers at each other, really. We need to be able to make buildings work.
I come back
Yeah.
to the I think generally right actually. And so, in fact, we were finding that branding genders building mix themselves is coming outside for that show the next but in terms of delivery side, public procurement is still the biggest hurdle that and association over both key ones fixed, alongside price, list of qualifications, and that is where so I see it every single day, where the actual delivery of it and getting that data in the factors who are dealing with seeing inflation, struggling themselves, we have to have a bit of flex in our system to make sure we still get carbon benefits related.
Actually represent the carbon benefits that we are achieving rather than I said we would have done years ago.
No, I was going to add a point as well, this, because I know a couple of times we've talked about everything's higher or lower compared to what. It's always compared to what. And on quite a few occasions, we talk about being compared to a gas boiler, for example. I think you mentioned before, you're in the TM65. Like, well, if we've already made the decision that we are not going to be getting fossil fuels in our buildings for our net zero future, then why would we do a comparison back to a technology and a solution that we can't use anymore? Really, the counterfactual should be something that actually is long term rather than something that we're trying to move away from. So I think that's something we should all do, because we talk about operational costs and everyone says, oh, it's going to be more expensive than running my boiler. Whereas, well, actually, you can't really run your boiler. That's not the right thing to compare it to. So maybe we should look at it against something else. I think that's something we all subconsciously do sometimes. We need to find the right counterfactual.
The new part has just introduced the baseline being a heat pump instead of a boiler for non-domestic schemes. So yeah, it's already being the new norm.
So we have a question here from online. It says there's other benchmarks that have already been established. In the example they give is LETI. What is your opinion on how they've developed, and do you think they're useful? Is it again a question of, because things are still so fuzzy, are they still a bit of a grey area not to be trusted? Or I guess, yeah, onto the floor, what's your opinion of the?
I mean, first of all, I guess all benchmarks, to actually look into them, you'd have to look at the background of the evidence base. I would say to kind of put targets and benchmarks out there, there definitely would have to be some strong backing behind it to publicly say, this is a benchmark that we set. I think it definitely can be useful, because from what I see from the LETI targets, for example, it's not setting one embodied carbon benchmark or target for all schemes. At least it's breaking it down into different sizes of schemes, different typology of schemes. And we all know, like, every building typology is going to operate differently, its components are different. So I think just having those initial figures in your head is always beneficial. Also looking at just the main structure of the building, which always has the massive impact on embodied carbon. So whether we're looking at just carbon versus steel versus timber, these are all things that, unlike MEP, which is more of a new thing in embodied carbon, materials, architectural materials have been around for quite a while, calculating the embodied carbon of them. So I think those numbers can still help us make really informative decisions.
So it's generated the conversation, hasn't it? Whether the benchmarks are appropriate, not appropriate, or what have you. The point is that we're all talking about it. Events like this are happening partly as a result of that. The likes of those documents. So at the moment, certainly a good thing as far as I can see.
I think for the LETI targets, an important thing to remember is that GLA is more like a top-down, whereas LETI is like bottom-up. This is the figure that we need to achieve if we are going to be net zero. So they're not really thinking about the practicalities of, oh, this design would achieve this value, would achieve this benchmark in a way that maybe like the GLA is kind of creating. What can we do now? So it's not necessarily a realistic figure. It's maybe something we're looking more forward in the future. And I think it's a figure that really should be used by manufacturers to see, okay, no, actually, we need to do more things and reduce the embodied carbon of our products to be able to hit this as an overall building. But at the moment, I don't think they're as realistic. When you have to get a bit.
We're trying.
It's hard. We try to get on building, break it down. What type of building, what systems, what structure would actually achieve this?
At the end of the day, it comes out of aspirations. And that's what benchmarks do. They're currently setting the aspirations for this generation of buildings. They will get updated as we go on. And that benchmark needs to be a way anyway, so that there is that performance improvement that they're able to deliver. No point achieving the benchmarks because you've done the best you can at that stage and then falling flat later on. So it's good to have that distance between the benchmark and your actual target building.
Awesome. Time for one more from the audience if we have one. Yeah, go for it.
It's a general question. That's in my head. So we talk about the benchmark system. Very debatable, and then I think methodology wise it can become more clear to see what they use the process is about. What we don't talk or discuss much is about the scope of calculation, because it evolves quite a lot from early design stage, stage 3, stage 4, especially with the systems which you don't have any information about it until you reach to the design stage. So if you look at the benchmarks, they also have different boundary conditions and different scopes depending on if it be METI or EA or GLA. So it's really hard for you to do a parallel comparison of our own results against that, because you think, okay, from the service perspective, we are considering every single thing, systems, components, because if you think about everything put in the building has embodied carbon, so you should calculate everything. And it's such a very sensitive calculation, because if you do stage 2, 3, and 4, you see the numbers increase quite a lot. And the only excuses we have is that we are now having more data, more scope. So what's your perspective in terms of challenge of calculation if you compare the scope you're looking at different design states? Yeah.
So just to repeat that, it's a question regarding how do you, I guess, effectively calculate embodied carbon across different design stages when inevitably the amount of embodied carbon increases as you learn more details about what you're putting
in. So, GLA guidance that you model 95% of your cost plan for each building element category. So, that's not possible at all stages. Stage 2 for M&P, what's the chances that your design is fully decided and costed? Very little. And I think that applies. But as long as you follow that methodology and you're honest about what the cost plan of the stage is, then that is consistent in itself, that has progressed with the design. It's not, it goes back to the idea that these are not 40% figures, these are estimations, and you can only do at that stage. I think as long as you represent your sources accurately and represent your scope, then that's fine. Which that comes with kind of clarifications, and it's difficult when you just say a number. When certain companies publish numbers, it's just a number. There are so many clarifications that come alongside particularly so many exclusions. So maybe the template wasn't available for them. It's common, but it's going to be a year later. It's going to be you will ultimately install that product. How would you do this on site? And spoke manufacturer, you don't have so there are so many clarifications. I get the nerves when people do just report just a figure. As we said, there are so many exclusions that, from my perspective, someone else got a different. Don't think around that at the moment.
Yeah, I think one thing is the exclusions part. So I think when we look at MEP, for example, the reason why the TM65 came through and what was like identified as such a gap was either we saw projects using just an X figure kilogram CO2 for any MEP system, or it was just excluded. It's like we don't have data points for it. So that's the first step. That's even if it's in the early design stage, not saying, well, we don't know, we can't include anything. Whether it's a generic system type at this point, like looking at the TM65 documents or other data sources that are available, even if it's, a generic heat pump, at least it's not just any heat generation equipment because it varies. So that's one thing. And then I guess, the different documents set their kind of boundaries, what they are. So GLA has the boundaries that are very specific. And if we go all the way down to the component level, EPD sets its system boundary very specifically. TM65 has a different system boundary, but that's because it's just easier to do than EPD at this point. And I would say, I guess the general answer of where we want to get to is like the industry consensus of what the boundaries are. And I do know that there's kind of a net zero standard which is being worked on in the industry with Lefty and many other collaborations. And that's hopefully something that's going to help to define the answer to this question, which I think everyone kind of comes up with at some point.
I think just to add, you do have the 95% threshold, but again, it's about the meaningful data that comes in at that point. So if your design isn't developed to a point, so if you're at stage 2, stage 3, you know there's room for further development. So then it's technically not a hard 95% at that point. So the percentage is a lot lower. So it's probably almost setting your thresholds in a project where you know for a fact that your design is developed to a point where it gives you meaningful data that you can then look as a representative for and closer to what your as-built might be. Obviously, there's going to be variations because when it comes to construction and the rest, material availability and the rest will play a big role. But it finally, I think, comes down to, especially with the variations in scopes. I mean, that is a critical thing. That's one of the critical flaws in the way it's currently working is different scopes. I think there has to be a clearer definition, because I think one clear aspect that the scope doesn't cover is who owns the carbon. And it is when you effectively take control of something, and when they take control of that carbon, it's not very clear. And that's getting clearer purely because it's finally coming down to commercial transactions. When do those finish? When that carbon transfers, and what carbon is that coming across? So that's why the scope lines need to be a little clearer. And I think at the moment, the only thing you can do in terms of design development is when it touches that 95% overall, that's when you almost pull a trigger for an assessment just to see, okay, this is more representative for my model, rather than you will do it at the early stages because they are your guiding models, but then you've got something a little closer at the end.
We're doing that actively now at early stage projects where we can't give you an exact figure, but I can tell you that solution A will be lower embodied carbon than solution B. And if you're writing your energy strategy for your project and that is of your consideration, then at least we can provide some indication that solution A will be lower than solution B. We'll worry about exactly how much lower or you know what that will implement. But yeah, we have been able to do that to a certain extent. But yeah, depends on how much that then changes to stage 3 and then stage 4 again.
So much easier. Spatial involved. So I think has to be based. You can't go too tight. Really, you have to have some flexibility. Make sure your curve on your carbon forecasting is realistic. Solutions. Carbon goes up. Why is that fun? You can't just explain it. You've got the detail. You have the room for genders initial. With that line, I think will be.
If it was easy, it wouldn't be any fun then, though, would it?
Yeah. Right. Well, thank you very much. Thank you everyone for coming. Thank you to the people who joined online. We've recorded it all, so it's all online. It will be on YouTube shortly. We've got our slides as well. So yeah, thank you very much. Thanks, guys.